How is everyone? Okay, I turned chat on. Okay, so I think we can get started. Let me share my screen and then we'll just go right in. Wrong share. Okay. I don't know what code OJ is. Cool. So this week is our last week, unfortunately. Week 4, we're talking about factors, combinations, and miscellaneous up to request. So if y'all have anything you want to do at the end of class, I'll try to get to that. All right. So I didn't want to do this, but I do have to go over some announcements. First off, thank you for our contest winners. Thank you for everyone who participated. This is the top 10 individuals. I think the highest score was Alex, who got a 22. And the results, problems, and answers are all on the website at this link. Okay. Thank you for everyone who competed. If you want to get there, you can go to the tab that says Math Contest, and then each of those tabs has a different thing. And there are 2 weeks of special classes, so there will be two or three new instructors teaching these classes, and they're actually going to be really interesting. So I really recommend you going to those. These will happen after this week. So next week and the week after. Okay, so enough of that. Our agenda for today is factors, class survey, combinations, and then request if time. And combinations if time too, because I don't know if we'll get to that. All right, factors. So last time I was going to do factors at the end, but I never got to it. So we're going to explore 4 things. First, the number of factors. Second, explore the factors of factorials. Third, find the product of factors. And then fourth, sum of factors. Okay, so first off, for number of factors, I'm sure many of y'all have already seen this. First, you just find the prime factorization, which we should be good at because we know divisibility rules and all that. Then afterwards, you take the numbers, prime factorization, add 1 to each exponent, and then multiply those numbers together. So in this case, 12 equals 2 squared times 3 to the first. So that means that 12 has 2 plus 1 times 1 plus 1, or 6 factors. Any questions so far? This may be reviewed to a lot of you. Okay. So let's talk about why that formula works. So put in chat or Q&A, why do you think that formula works from before? Adding 1 to the exponents and then multiplying those together. And then once you're done with that, then try answering the second question, which I think should be easier. Let me pull up Paint real quick. Okay, yeah, I saw a lot of right answers for the second question. And I see a couple for the first question. So I guess I'll do the second one first. For the second one, we know that the number of factors will be odd. We'll talk about it in 2 different ways. First off, let's look at perfect squares. I'm sure This is what a lot of you guys said. So perfect squares, and I'll take 16 as an example. So 16, how many factors does that have? Is 5, right? 1, 2, 4, 8, 16. All the powers of 2 less than or equal to 16. So this is 5 factors. And you'll notice that each pair of these match up. So the smallest one goes with the largest one. The second smallest goes with the second largest because they always multiply to 16, right? So we always have factors that come in pairs unless there's a factor that doesn't come with a pair, with another number, which means it has to come with itself, which means that if there is an odd number, if there's an odd number of factors, there exists one number that pairs with itself, which means that the number is that number squared. So it would be a squared, right? Even is just if the number is not a perfect square. So that's the explanation using just like looking at the factors, using the formula, which is write it in its prime factorization, then add 1 to the exponent. We would get 5. And this number is always going to be odd if all the exponents are odd. All the exponents are even, because if all of these are even numbers and I add 1 to them, then they all become odd numbers. And if I multiply them, it's going to be an odd number. Does that make sense? Any questions? Okay, so that's the second question. The first question was, why does that formula work? So why can I, to get the number of factors, just add 1 to the exponent, then multiply those numbers together? I saw a couple right answers. So thank you for those answers. The reason is, if I can write my number n as like p1 to the a1 times p2 to the a2, and so on, all the way to pn to the an. These are just variables where all of these are primes, and then a's are the exponents. Then any factor, so any factor has to have the form of p1 to the something times p2 to the something, and so on, all the way up to p of n to something. So it wouldn't be possible to have another prime like p to the p of n plus 1 be a factor of n, because this prime never even showed up in the factorization. So there's no way it can exist in the prime factorization of a factor. Okay. And we know that all of these exponents have to be less than their corresponding original exponents. All right, for example, if I had 2 squared times 3, one of the factors can't be 2 cubed. Sure, 2 was in the factorization, but 3 is way too big. 3 is bigger than 2, so it can't be a factor. So the number of possibilities for this factor, for this exponent, are 0, 1, 2, all the way up to a of 1. And that is a of 1 plus 1 possibilities. Similarly, I can do the same thing for all of these. And what I end up getting is there are a of 1 plus 1 possibilities for the first one, then a of 2 plus 1, and so on, all the way to a of n plus 1. So that's where the formula comes from. Okay, any questions? Cool. So let's try it out. Factorize these and then find the number of factors. I'll give y'all a minute and a half to do this. Yeah, and if you want to, you can just put the number of factors instead of like the whole thing. But I appreciate it. Okay. So I'm guessing that some of you may still not be familiar with the formula, and I kind of went fast with that, so sorry about that. For number one, 48 equals, I know it's 8 times 6. 8 is 2 cubed. 6 is 2 times 3. So I can write this as 2 to the 4th times 3. And that's what I mean by factorize 48. So this is the prime factorization. And then find the number of factors. So all I do is add 1 to this exponent, add 1 to this exponent. And notice that I wrote a 1 here because 3 to the first is just 3. There's like an invisible 1 there. So if I add 1 to 4, I get 5. Add 1 to 1, I get 2. So I multiply those together and I get 10. And I can verify that this is true. The factors of 48 are 1, 2, 3, 4, 6, 8, 12, 24, 48. And I think that, oh, I missed one. Did I? Oh, oops, 16. Yeah, so that's 10 numbers. So we know that this formula works. I'll give y'all 30 more seconds for the other ones. All right, nice. I'm getting more answers now. Okay, while I do the second one, if you're still working on the third one or fourth one, go ahead. 560 is 8 times 70. That's 8 times 2 times 5 times 7. So I can write that as 2 to the 4th times 5 times 7. Oh yeah, and I would recommend always factoring in this way. You don't want to factor out you don't want to factor out a 5 from this number. Even though that you know for sure 5 is a factor, you want to first split it up into easy factors like that, and then once you're at a certain point, take out the 5. But if you took out the 5 here, then you would end up with like 5 times 1, 12. And 112 is way harder to factor than 8 and 70. So that's just a quick tip for getting faster. Okay, I see enough answers for number 2. Here what I do is add 1 to all of those, so I get 5, 2, 2. Then I multiply them, and I get 20. So 560 has 20 factors. 48 has 10 factors. So we're halfway there. What about the next number? So how would I factorize that? For those of you who just came, I'm talking about the number of factors, and to get the number of factors, first you prime factorize it like so. Then you add 1 to each exponent, and then multiply those numbers, those resulting numbers together. Okay. Yeah, there's actually many ways to go to do this one. So you could do 9 times 111, or you could do 99 times 10101, or 999 times 1001. All right, so there's 3 different ways. These 2 are kind of similar. I think this one would be pretty hard because 10101 is kind of hard to factorize. So I'm just going to delete that. I'll just go with the bottom one because we end up kind of doing the same thing. 999 times 1001, we can write that as 9 times 111 times 1001. And 9 is 3 squared. I mentioned before that they like to use the number 111. 111 can be written as 3 times 7. 3 times 37. And 1001 is, as I mentioned before, I think the first class is 7 times 11 times 13. If this is your first time seeing it, you can just remember that 111 is 3 times 37, and 1001 is 7 times 11 times 13. Cool. So grouping them together, I get 3 cubed times 7 times 11 times 13 times 37. Now I'm going to leave out that step, that intermediate step. I'll just do 4 times 2 times 2 times 2 times 2. So this becomes 64. And yeah, I saw a comment saying that we could write this number as 1 million minus 1 and then use difference of squares, which would get 1000 squared minus 1. And we would end up getting, yeah, so that's a more formal way to get to 999 times 1001, or just a slicker way. All right, and are there any questions about how or what I did over here? All I did is add 1 to the 3 exponent to get 4. And then for each of these, if I add 1 to the exponent, I get 2, because the original exponent was 1. And there's 4 of those numbers over here. So I would end up just doing 2 to the 4th. So my final answer for the number of factors is 4 times 2 to the 4th, or 64. All right, and the last one, 4298. I can recognize the 7 in here because 42 is divisible by 7. 98 is divisible by 7. And there's definitely a 2 in there. All right, so that's my final factorization after checking that this is prime, which it is. And in this case, if I add 1 to all the exponents, I just get 2 cubed. So 4298 has 2 cubed factors, which is 8 factors. Are there any questions about that? Oh, how did I check that 307 is a prime number? I actually may talk about how to check how numbers are prime. Maybe like for a minute or so after combinatorics. Good question, but you can use Google if you have that. But if you don't have it, there's a method for checking it, but it's basically just brute force. You have to check all the small primes, make sure that 307 is not divisible by them. All right. Those are the answers. Are there any remaining questions? Awesome. And don't be afraid to ask. Oh, is there a typo? Oh, oops. Yeah, that was supposed to be a 5 over here. I guess I did it wrong as I was typing this up. Thank you. All right. So how do we get faster at this? Well, everything we did here is actually pretty simple. All we're doing is factoring. So we get it into a factored form and then multiplying. So what you need to practice is your divisibility rules. So this helps you get faster. Memorize and recognize special factorizations. So in this case, I would definitely memorize that like 48 is 2 to the 4th times 3 to the 1st. I would definitely memorize that 560, or no, I'll just say 70. I would definitely memorize that 70 can be written as like 2 times 5 times 7. I would definitely memorize that 111 is 3 times 37. And I would definitely memorize that 1001 is 7 times 11 times 13. So that's what I mean by memorize and recognize special factorizations. This actually gets you much faster. And at the same time, if you're going to be doing that, you have to remember multiple things at the same time. So let's say I wanted to do number 3 in my head. So I would probably break it up as 999 times 1001. So in my head, I have those two numbers. I'll first focus on 999. So this is equal to 9 times 111. And 111 has a factor of 3. 9 has 2 factors of 3. So I just have to remember that there's 3 factors of 3 in total. So I end up getting for 999, 3 cubed times 37. I just have to remember this after I'm done doing 1001. Otherwise, I would end up having to go back and then verifying that what 999 is. Sorry for stuttering so much. Anyways, yeah, so you can see that in a lot of these places here, you could not go through the work and then directly skip over to a factorization. And of course, doing a lot of practice helps. Awesome. So there's a special problem that I've seen a bunch, and I think it's pretty interesting to talk about. So Here we're trying to find the number of factors, or just actually factorize a factorial. So I'll start off with the definition of factorial in case you haven't seen it. A factorial, which is represented as an exclamation mark of a number, is the product of all positive integers less than or equal to that number. So I would say that n factorial is the product of all numbers less than or equal to n, or in other words, n times n minus 1 times n minus 2, all the way to 1. 2 times 1. Okay, and I'm guessing many of you have seen this before. So for example, 1 factorial is 1. And I should mention that 0 factorial, we define that as 1 as well, even though it doesn't really make sense to have positive numbers less than 0. So we just put that in concrete terms. 2 factorial is 2 times 1 or 2. 3 factorial is 3 times 2 times 1, 6, and so on. And I definitely recommend you to memorize these first 7. Past this, the numbers are pretty big. Okay. Yeah, I guess there are actually many ways to prove why 0 factorial should be 1. So here are 3 problems. All I'm asking you to do is write out the prime factorization of these. Oh, the Q&A has questions. So there are many ways to approach this. I'll be talking about the fastest way to approach it for big factorials. So number 3 would be one of the questions I would use with the method I'm about to talk about. Okay, 10 more seconds. Cool. All right, 3 factorial is pretty easy because 3 factorial is 3 times 2 times 1, which is just 2 times 3. All right, so that's my factorization. Awesome. We have a score of 33 right now. All right, second question, factorize 6 factorial. So I'll write 6 factorial as 6 times 5 times 4 times 3 times 2 times 1. Right? And I can break up each number into its prime factors. So 6 is 2 times 3. 5 stays as 5. 4 is 2 squared. 3 is 3. 2 is 2. And then 1, we don't worry about that. All right, and then grouping these together, I get 2 to the 4th times 3 squared times 5. Are there any questions about how I did that? Okay. And if you were trying to do this in your head, as I said before, having really good memory or being able to remember like what or how many 2s you had, how many 3s you had is really useful. Okay, and then the last one is 15 factorial. So here, I'm not actually going to do it, but using the way I've done just now, I would have to write like 15 times 14 all the way times 2 times 1. And then write out 3 times 5 times 2 times 7 and so on. So this is actually very, very inefficient. And for even numbers like 10, it's going to be very hard. So what do we do when we have a question like factorize 15 factorial? Yeah, so this is the answer that you get. And if you did it the method I'm about to using the method I'm about to talk about, then hopefully you got this answer. Okay. So here's the method. And it's everything from this line downwards. I kind of wrote this like a for loop. So for each prime less than the number n, let's just call this prime p. And then first we find the floor of n over p. So let me first clarify that the definition of floor. The floor of a number is the greatest integer that is less than or equal to x. So for example, the floor of 3 is 3 because 3 is the biggest integer less than or equal to x. Sorry, 3. The floor of pi is also 3. The floor of like 5 over 2, that'd be 2. Oops. And like the floor of a negative number, so like negative 2.5 would be negative 3. Okay, so this isn't too important. I just want to make sure that we all know this definition. In the slides, I'll refer to it as floor. Okay, so first find the floor of n over p, and we'll just call this number a1. Next, find the floor of a1 over p, so this value over p, and we'll just call this a2. And we keep doing this. So when do we stop? Well, at a certain point, we're bound to get some a to be 0. Like let's say my p was 5 and my a1 was 3. Then a2 would be the floor of 3 over 5. So floor of 3 over 5. And this is, of course, 0. Now, if I kept trying to find the floor of 0 over 5, I would keep getting 0 and so on. So it doesn't actually matter. So I only have to do it until I get the value 0. So we keep doing this, and then the exponent for this prime p is the sum of all the a's. So a1 plus a2 plus a3 all the way to whatever you reach. And this doesn't really this might not make sense in words, so I'll show an example here. The question is factorize 5 factorial. All right, so we go through the process. First, we have to do this for each prime less than 5 because n is 5 here. So first, we'll just start with 2 because 2 is a prime. I have nowhere to move the zoom thing. There. So 2 is a prime. So I first start off with A1 using the variables from before. I get 5 over 2, which is 2, right? The floor of 2.5 is 2. Then my A2 is the floor of this number, or A1 over 2. So that's floor of 2 over 2, which is 1. And finally, I know that this number is going to be 0 because if I'm doing a number 1 over 2 and then flooring that, then this has to be 0 because 1 is less than 2. So I can actually do this process until I get a number that's less than whatever the prime is. In this case, the prime is 2. So once I reach 1, I can just stop there. All right, so here I have 2 and 1. I add those up, I get 3. So the exponent of 2 in the factorization of 5 factorial would be 2 cubed. Okay, so we just have to remember that 2 cubed is here. We move on to 3, and then I won't use the whiteboard anymore. 3 is a prime less than or equal to 5, so we take the floors. 5 over 3 is 1. 1 over 3 gets 0, so we just stop there. So the exponent of 1 would just be 1. The exponent of 3 would just be 1. So we have 3 to the first now. And finally, 5 is the biggest prime and the last prime. That's less than or equal to 5. So we take the floor of 5 over 5, which is 1. Then 1 over 5, we don't have to do that. So the exponent of 5 is 1. So we also get 5 to the first. Therefore, our factorization is 5 factorial equals 2 to the cube, 2 to the third times 3 to the first times 5 to the first. Are there any questions? And we'll do this again for a few more. So before we get to that, first off, why does this actually work? Well, if I can show that this idea works for 2, then you would believe me that it works for 3 and 5 and all primes, right? So I'll just show that this process works for finding the exponent of 2. And another note is that I wouldn't actually write all this out. In my head, I would be doing 5 over 2 is 2. I divide that by 2, I get 1. And then I just sum those up and I get 3. So I wouldn't actually write out all of this. Yeah, I'll go back to the other slides. So before that, to get the exponent of 2, what I'm doing is I'm looking at the numbers from 5 through 1, and then seeing how many of these numbers have a factor of 2. So my first question is, how many of these numbers are divisible by 2? My handwriting. Okay, well, every other one is going to be divisible by 2, so I have 2 here. And in general, actually, the number of numbers divisible by p, if I replace 2 by p, would be the floor of n over p. In this case, it just happens to be that p is 2, n is 5, so the number of numbers divisible by 2 would be 5 over 2, and then floored. All right, so for each of these numbers that are divisible by 2, I've now counted using this number. Let me erase this real quick. This number now tells me that each of these numbers has at least contributes one factor of 2 to the total number. All right, so I've now contributed 2 factors of 2. So that's where this red 2 comes from. But I also know that numbers like 4 contribute 2 2s to the factorization. I've only counted 1 2. So then I have to look at the numbers divisible by, oh no, divisible by 4. And this would be the floor of 5 over 4. And actually, this is the same as the floor of 5 over 2 over 2, then floored. So it would be the same thing as dividing this number by 2, then flooring it. So I would divide that number by 2, I get 1. The floor, I still get 1. And then here I can stop and I get 3. I know that none of these numbers from 5 to 1 offer a factor of 8. Right? None of these numbers have a factor of 8, so I don't actually have to do anything past this. And I would do the same thing for 3, for 5, and I ultimately get a simplified formula, which is this. Okay, cool. At this point, let me find it real quick. Hopefully you didn't see those answers. Okay, so let me send this out. And yeah, I would really, really appreciate it if you could do this. Let me send it to chat real quick. And I'll answer any questions or comments you guys have. Hello. And if you want to take a break now, instead of doing the survey, I mean, sure, if you want to. So just make sure that you fill out number sense over here, and then overall class satisfaction, excellent. And then besides that, everything's good. No, I'm just kidding. Oh, no. Okay, so I'll give y'all 2 minutes to do that. Is that enough? I thought I sent, okay, let me send it again. I was just kidding about that, by the way. I have to remove this. This is not actual. Like, it's not actually a poem about those. Oh, this is actually not the end of class either. We're going to have a bit more. All right, so I'll go back to it. If you're still working on it, that's fine. All right, so when do we use this? We use it for large values of n, so large factorials, and then practicing this a lot will make the process very fast. So try these out. We have 10 factorial, 12 factorial, and 20 factorial. All of these numbers would be hard to factorize if we just like listed out 10, 9, 8, all the way down to 1. So here we want to use the formula, the process from before. Okay. For the first one, we have 10 factorial, and the primes less than or equal to it are 2, 3, 5, and 7. I can safely write these down because I know that all of these appear at least once inside 10. Oh, oops, 10 factorial, I mean. Okay, and I know there won't be any other prime factors besides these 4, so I'll just start with 2. 2, I would have 10 divided by 2 florid is 5, plus 5 divided by 2 florid is 2, and then plus 1. So this would be 8. For 3, I do 10 divided by 3 florid is 3. Then 3 divided by 3 florid is 1. So that would be 4. For 5, 10 divided by 5 is 2. I can just stop there because 2 is less than 5. And then finally, 7, 10 divided by 7 is 1. Okay, and then to find the number of factors, I just add 1 to each one. So I get 9 times 5 times 3 times 2 factors, or 9 times 30, which is 270 factors. Okay, I saw a lot of people got this one. For 12 factorial, this is going to be 2 times 2 to the something times 3 to the something, 5, 7, 11. I know that these are going to be the primes in the factorization. So for 2, I have 6, then 3, then 1, so 10. For 3, I have 4, then 1, so that's 5. For 5, I have 2, 7, 1, 11, 1. Y'all understand how I got these numbers? 6, 3, and 1. Can't see my mouse. Oh, there it is. Okay, and then the number of factors is 11 times 6 times 3 times 2 times 2, which is 11 times 72. And we can do that. That's 792. Okay, and our last one, 20 factorial. It's bigger, but it's not, it's still like the same magnitude of difficulty as the other ones. 20 factorial is going to have 2, 3, 5, 7, 11, 13, 17, and 19 in it. And actually, I know straight away that all of these are going to have powers of 1. So I actually don't have to like write anything out for it. They're all going to have factors of 1 because the next smallest multiple of 11 is 22, and 22 is not in the representation of 20 factorial. So I'll start with 2. 2 is 10, then 5, then 2, then 1, which is 18. 3 is 6, then 2, so 8. 5 is 4, 7 would be 2. And then to find the number of factors, I just add 1 to each of them. And I think the number was like 41010. I did not. 41040. Okay, I didn't actually like multiply that using a trick. Okay, any questions about that? All right. And I guess we'll only get to this. So for the product of factors, the formula is n to the a over 2 if a is the number of factors. So this directly uses what we are just doing. Here n is the number, a is the number of factors. For example, if n is 12, if my number is 12, then the number of factors would be 6. We did this before. And the formula would be 12 to the 6 over 2, or 12 cubed, is 1728. So how do you get faster here? Well, I think really the main thing is to get fast at doing finding the number of factors. If you can do that, then product of factors is really easy. And then you may notice that sometimes a is going to be odd. Specifically, when n is a perfect square, then a is going to be odd. So what do we do then? 36 has 9 factors, but our formula is 36 to the 9 over 2. We can write this as, says over here, 36 to the 9 times 1/2, or 36 to the 1/2 whole thing to the 9th, and that's just 6 to the 9th. So of course it has to work for all numbers, so it can't just not work for perfect squares. And here's I guess you can look at this list right here and then see why that works. If I have 6 factors and I try pairing the first and last sub, second to the second and last, third to the third and last, then I get 3 pairs of numbers, or 6 over 2 pairs of numbers. And each pair of those numbers multiplies to 12. Right? So that's why I have 12 to the power of the number of pairs, or a over 2. Okay. So why does it work? Yeah, we just did that. Find the product. If we have time, I'll get to this, but I don't think we'll have time. All right, and then for the sum of factors, this is a bit harder to do in your head, and it's harder in general. So we use the prime factorization here. So if n's prime factorization is this expression, where all the p's are primes, and then these a's are just the exponents of those primes, then the sum of n's factors is, and what is happening here? Well, for each prime, hello? Right. For each prime, I add up the highest exponent. So I'll just go through the example below. 12 equals 2 squared times 3. So for each of these, I go down the list. I just add up all the primes, all the powers of 2 less than or equal to the highest one. Right? So I get this number from that. And then for 3, I do the same thing. And what I end up getting is 4 plus 2 plus 1, or 7, times 3 plus 1, or 4. And that's 28. And the example for 36 is here. And the reason it works is kind of similar to the reason why the way to count factors works. We just look at the number. We look at this expression, or this way of representing each factor, and then we can factor out this term from it, then we can factor out this term from it. And essentially what we're doing here by writing out the sum as this is we can choose an exponent for P1. We can choose an exponent for P2, and so on. And that's basically what we're doing by multiplying all these terms together. We're basically only choosing one exponent. That was kind of confusing, but I'll just go through the answers here because we don't really have time. I want y'all to have a break. So the sum of the factors of 28 would be 7 times 8, because we can write 7 or 2 squared plus 2 to the first plus 2 to the 0, which is 7. So that's where this 7 comes from. And then for the other 7, for the other power, that's 7 to the first plus 7 to the 0. So that's just 7 plus 1, or 8. And that's where this 8 comes from. Yeah, so just a fun fact to note is that 28, the only two numbers that are small and have a sum of the factors equal to twice their number is 28 and 6. 6 has 1, 2, 3, 6, which is 12. 28 here we can see is 56. All right, anyways, enough of me talking. I want to thank everyone for coming to this class. It means a lot. I really enjoyed making these, but to be honest, I made these like an hour before class, so sometimes the quality is not very good. But I do really hope that y'all learned at least something from this class, whether it be like a way of thinking or just like some formulas if you haven't seen these before. And yeah, I hope you have a great time in physics, which is coming up, and I'll see you guys if we ever do a class again. I'll make Rochan host.